Okay, probably welcome back. This is going to be the last of the three sections of 5.3. I'm not sure I'm going to get through all of this last section, but we're going to pick it up on problem 14, and I set myself some room here to do 14, but I need more room, so we're going to ignore that 16 is on this same page. Okay, I had a student come in this morning, and she wanted me to work through her work with it, and this got ugly in a hurry when we were finding the second derivative, and I think it's still not going to be a real pretty thing when we find the second derivative, but I think if you struggled on it, I think this is going to help. So find all points of inflection. Points of inflection occur when the slope, or excuse me, when the second derivative is 0, and could occur when the second derivative is non-differentiable, like on y equals x to the 1/3. By the time I take a second derivative, I definitely have a negative, so I have an x in the denominator, and the graph of that looks like this, and clearly we have an inflection change here. We're cupping up, cupping down, so 0 could be a location of an inflection point. So we're going to find the second derivative. I'm going to think of this as x times 9 minus x squared to the 1/2. This is a load of an algebra problem. So y prime equals, this is a product rule, so there's going to be a plus in there along the way. So it is the just plain old first times the derivative of the second. That's 1/2 9 minus x squared to the negative 1/2 times the inside derivative, negative 2x. And it's so tempting to move on from there, but that's just half of the product rule. There's going to be a plus. I've done it. I'm sure some of you have done it as well. It's easy to forget that second half. So derivative of the first is x times the just plain second, 9 minus x squared to the 1/2. And at this point, I'm going to simplify this, and then I might do something different than what you would expect here. When I simplify this first term, the 2's cancel, the negative lives, and I've got an x squared, 9 minus x squared to the negative 1/2, plus 9 minus x squared to the 1/2. Now, the first time I did this problem last week, I went ahead and then I put this over there, I got my common denominators, smashed things together, and then I went quotient rule. And I got through it, but it was a mess. And at some point going through it, I'm like, oh, I'm going to go back and do this again, and I'm just going to leave it like this and find the derivative of this with product rule involved. Okay? How many of you went through that problem and now did get it all as one big fraction and then quotient ruled it? It got ugly. All right, this is going to get ugly too, but I think it's a little bit more manageable. So we just have to be open to what our options were. What's the benefit of getting this in a fraction? If I had to find places where the slope was 0, if I was looking for those critical points, then getting this as a fraction would be helpful. But I think maybe second derivative of this, it's going to be bad, but I think it's going to be better than if we smash this together as a fraction and go quotient rule. So is it clear? We still have a product rule here. So I want just plain first, negative x squared times derivative second, times negative 1/2, 9 minus x squared to the negative 3/2, reduce it by 1, times negative 2x. That's just half of the product rule, plus the derivative of the second is negative, or the derivative of the first is negative 2x, so minus 2x times the just plain second. That's the second half of that product rule. I still have to take the derivative of this term, plus 1/2 times 9 minus x squared to the negative 1/2 times the inside derivative, and I get that. And you're thinking, wow, that's terrible. Well, people who are thinking that are the people who haven't tried it with quotient rule yet. All right, let's clean some things up. I've got a negative times a negative times a negative. Negatives win. 2's cancel. I've got 3 x's, x cubed, times 9 minus x squared to the negative 3/2. Minus, I don't think I can clean this one up anymore. 9 minus x squared to the negative 1/2. plus times minus, minus, 2's cancel, x times 9 minus x squared to the negative 1/2. 3 terms, but 2 of those terms are like terms. I've got an orange, and I've got minus 2 apples, and I've got minus another apple. Ugly apples, but you see what I'm saying? Like terms there. So I'm going to combine those. Negative x cubed times 9 minus x squared to the negative 3/2. I've got minus 2 of these things, minus 1 more of these things. I've got minus 3 of these things. And now you want to go common denominator. Great. I'm not even going to do that now. I could put this over 9 minus x squared to the 3/2 and this over 9 minus x squared to the 1/2 and then get common denominators. And I think that's just as viable as what I'm going to do. But I'm going to take it back. Let's go back algebra days. 3x to the 3rd minus 4x to the 5th. If I was going to factor this, I would factor out a what? X cubed, and I'd get 3 minus 4x squared. But the key is I factored out the smaller number of x's. Well, of these things, my smaller number of them is negative 3/2. But let's take a look. This term and this term, I am going to factor out a negative. They both got one to give. I'm going to factor out an x. They both got a plain old x. And they both have these 9 minus x squared things. I'm going to factor out the smaller number of those. The smaller number between negative 3/2 and negative 1/2 is negative 3/2. And now I'm going to say, what do I have to multiply this by to get to there? Well, I got my negative. I definitely need a pair of x's. And I don't need any. I mean, I factored out the negative 3/2 here, right? Here to here. Well, I got the negative, so this is plus. I need a 3. I don't need an x. But I still need something to do with these 9 minus x squareds. Here's the big question. What goes there? I got negative 3/2 of them. I want negative 1/2 of them. To the what? What do I do with those exponents? I add them. 3 plus 2 is 5. Negative 3/2 plus what is negative 1/2? 2/2, right? Or 1. Just to the first. Again, you can get the common denominators, but factor out the smaller number of it. Let's see what we've got now. Equals negative x. I'm going to put this second. And I'm going to put this in the denominator in just a moment here. But I'm going to put this second. Here I've got x squared. I'm going to have minus 3x squareds here. Minus 3x squareds and a plus x squared. Minus 2x squareds. I get a plus 27 as well. And all of that is on 9 minus x squared to the 3/2. That's bad, but I don't think it's as bad as the, is that better than the quotient rule in it? Yeah, the quotient rule got ugly in a hurry, and it was, I wanted to work through it, so I did, but I went back and did it this way. I thought this was better. So, when is the second derivative equal to 0? When x equals 0, or subtract 27, divide negative 2, so that's 27 on 2, take the plus or minus square root of. When are we non-diff? At plus or minus 3. We got problems there. In fact, might have more problems. Nope, because it's never going to be negative if we stay between plus or minus 3. We could go back up to the very original here and talk about endpoints. Is it pretty clear that 3 is about the limit of how big I can get? Negative 3 less than or equal to x less than or equal to 3. Right? Here's good news. 27 halves is 13.5. The square root of 13.5 is more than 3. That's outside of our boundaries. So what do I need? Negative 3, 0, and 3. But these guys are just endpoints. Can an endpoint be a point of inflection? Can that endpoint be a point of inflection? Did the concavity change there? No, it just stopped. An endpoint can't be a point of inflection, so we don't have to test those. I just need to know what happens when I put in a positive. So if I put in, say, 1, what do we get here? I get a negative times a positive over a positive. 2 positives and a negative, I get negative. Let's put in negative 1. I put in negative 1 and I get a positive times a positive over a positive. Positive. Oh, okay. I've got an inflection point at 0. Put in 0 and we get 0 at 0, 0. That one's bad. That's a tough problem. I'd probably feel a little bit guilty about that one on a test. Okay, let's come back and let's take a look at 16 from your homework set. This one, what do you think? Think I'm going to product rule that? I could, but only if I wanted to make it harder. How about we just treat this like y equals 4x cubed minus x to the 4th? Wow. You expect from 14 to 16 to raise the level a little bit, but man, 16 is a breeze. Even product ruling this thing is a breeze. Y prime, 12x squared minus 4x to the 3rd, double prime, second derivative, 24x minus 12x squared. When is the second derivative equal to 0? I'm going to factor out a 12x, and I get 2x. Nope, sorry. Factor out a 12x, and I get 2 minus x. So x equals 0 and x equals 2 are possible inflection points. How about non-diff? No, we don't have non-diffs. There are no non-diffs here. And this function is continuous forever. End model behavior doesn't really totally help me because it doesn't talk about cupping. It just talks about does it go up, does it go down. So I'm going to go right to my y double prime. I'm going to put 0 on here. I'm going to put 2 on here. And I know that we get zeros there. Those are possibilities. And I just want to see, are we changing signs? So I put 1. I put 1 into what? Y double prime. I'm testing the concavity. I want to know, is it concave up, concave down? So if I put 1 into my second derivative, I'm going to put it into this one right here, that version. I get 24 minus 12, I get positive. If I put in 3, I get 72 minus 108. I get negative. If I put in negative 1, I get negative 24 minus 12. Yep, it's negative here. So I've got concave down, concave up, inflection point. It was concave down, concave up, inflection point. Inflection points, because then I'm concave up, concave down. The signs are changing. That's what I'm looking for. At 0 something and at 2 something. At 0, let's go back up. Put in 0, get out 0. And at 2, I get what? 8 times 2, 216, an inflection point. That's where we go from accelerating to decelerating. Okay, I think I'm building a little bit of lag, so I'm going to stop here and wrap up this on another video.